Hello, good evening, everyone. Welcome to the third week tutorial of this thermodynamics course. I am Tananga Sutia, and once again, I will be taking this class of the third week. So in this class today we will be doing last up till last class we were applying first law of thermodynamics in a closed system. In this class we will do some questions in which we'll apply first law of thermodynamics for an open system, in an open flow system. So let us proceed. Okay, so the first question is: air enters a diffuser of a jet engine at 20 degrees Celsius, 100 kilopascal, 300 meter per second. The inlet area is 0.5 meter square. The outlet area is such that outlet velocity is very less as compared to the inlet velocity, and there is no drop of the pressure. Calculate the mass flow rate of the air and the outlet temperature of the air. Okay, so diffuser. Okay, this is how a diffuser and compressor look. The only difference is between the inlet and the outlet. In the diffuser, it comes from lower cross-section area to a higher cross-sectional area, and in a compressor it comes from higher cross-sectional area to a lower cross-sectional area. So diffuser, what it tells us about, let us say that this is our inlet condition I, and this is our, say, outlet condition O. Okay, so this is how air comes and this is how air goes out. Okay, so what it is says that T at I is equals to my 20 degrees Celsius, and P at I is equal to my 100 kilopascal. Okay, and my V at I is equals to 300 meter per second. Now one more it is given, it's given is the inlet area. Remember, they can give also diameter, but now they do not want any sort of calculation. It's directly giving us as the area. If it is given as diameter, we know what is the formula to calculate an area: 0.5 meter square. Okay, now this is for the inlet part. This is what the first statement tells us. Then we are told here the outlet area is such that outlet velocity is very less as compared to the inlet velocity. That means what? That VO someone is joining. Okay, okay, so the outlet area is such that the outlet velocity is very less compared to the inlet velocity. This means that this is approximately equals to 0 in comparison to your inlet velocity Vi. Okay, and then there is no drop of pressure. That means P outlet is also equal to my P inlet, and that is equal to my 100 kilopascal. Okay, so now we have to calculate the mass flow rate of the air. Okay, so in order to calculate the mass flow rate, we have to apply the conservation of mass equation. So if I assume, where is the pen? Yeah, so if I assume this is my control volume, this whole area is my control volume. If I assume this whole area is my control volume, oops, sorry, it's not coming. Yeah, if I assume that this is my control volume, then the rate of change of the mass of the control volume will be equal to mi dot minus mo dot, where mcv is the mass of control volume, mi dot is the rate of inflow of mass, and mo dot is the rate of outflow of mass. Okay, so mi dot will be entering this side and mo dot will be entering this side. Now since nothing is mentioned, so and most of the thermodynamic systems which we study in engineering applications, if it is not mentioned, we apply the steady state condition, because whenever we apply these laws we mostly apply in steady state condition. So what will happen in steady state condition? Assuming steady state, what will happen? The mass change will not happen with respect to time. This will be equal to 0, which will implies that mi dot will be nothing but equal to mo dot. Okay, now we just need to calculate what is mi dot and what is mo dot. Now mi dot is what? It is the rate of mass flow rate in the inlet. So we know the inlet velocity vi, and we know the inlet area ai. Now if we do this two, what will we get? If we do this two only, okay, it will be meter per second into meter square. That means we will get meter cube per second, which is volume flow rate. Now if we multiply volume with density, what will we get? We will get it as kg per second, and we want is what? Mass flow rate. We do not want volume flow rate, that's why it's not aivi. It will be rather it will be into rho. Okay, so it will be rho ai vi. Okay, so it will be rho ai vi. Now we have vi, we have ai. Now how to calculate rho? Okay, rho basically in the inlet, rho I ai vi in the inlet. We don't know whether the density will change or not, it's not telling us anything, so we'll put it as rho I ai vi. Okay, so that is the mass flow rate at the inlet, which will be always equal to the mass flow rate at the outlet. Now not always, means in this case. Now we know vi, we know ai. Now to calculate rho I, we have to apply the ideal gas equation. Why? Because it is telling us that it is an air, and I have told you in the last class that if a gas is given and nothing is said about it, you can directly assume it as an ideal gas. Okay, if it is real, it will they will mention clearly in the question that it's a real gas. Now we know that ideal gas equations is what? P equals to rho r t. Okay, and in the initial state, everything I can put it was pi is equals to rho I. Well, r will be same for all, whether it is inlet or outlet, that's why it is, I'm keeping it as r, and it will be ti. So putting this value, my rho I will be pi by r of ti. Now we have pi, we have ti. Now we need what? R. And we all know, until now I think you have by hearted the value of r for an air. The air r value is 0.287 kilojoule per kg Kelvin. Okay, so we'll put it here. The pressure at this is 100 kilopascal. I'm putting in kilo because I will put it here kilojoule, or else you can do it with 10 to the power 3. It's no, it's okay. Okay, everything in SI unit into 10 to the power 3, then 0.287 into 10 to the power 3, and we have Ti. What is Ti? Is 20 degrees Celsius. Okay, 20 degrees Celsius will convert it into Kelvin. It will be 293. This will give you the density. Okay, let us calculate the density. 100 divided by 0.287 into 293. Okay, so the density is 1.189 kg per meter cube. Okay, so the density is 1.189 kg per meter cube. Now we'll just put it here. What is Vi? Our Vi is 300 meter per second. What is Ai? Our Ai is 0.5 meters square. And what is density? Rho I is my 1.189 kg per meter cube. So all this will done cancel each other and you will get at kg per second. Okay, so let us calculate this one. 300 into 0.5 into 1.189. It is okay, 300 into 0.5 into 1.189. It is 178.35 kg per second. This is the first part, answer of the first part. Okay, so very simple. We have to calculate the mass flow rate, and this will be the mass flow rate throughout the diffuser, whether it is Mi, whether it is m dot, or any part between this. Okay, now we have to calculate the outlet temperature of the air. That means here the temperature is Ti. We need to calculate what is the value at T0. Okay, let me put new slide. Okay, so yeah, okay, so the part B, we have to calculate T0. Okay, we have to calculate T0. Let me check whether my net is there or not. Yeah, it's working fine. Okay, okay, now next part is we have to calculate the T0. And for that we have done the mass balance. Now we have seen the first law of thermodynamics for a closed system, and I'm sure you have got the derivation of the first law of for an open system. For an open system, that is for the flow process, it is dEcV by dt, that is the change in energy of the control, rate of change of energy in the control volume, will be equal to Q dot minus W dot plus M1 H1 plus V1 square by 2 plus GZ1 and minus M2 H2 plus V2 square by 2 plus GZ2, where 1 is my initial state and 2 is my final state. 2 is my final state. Okay, but here we have already declared our initial and the final states. Our initial states were I and my final state were O. Okay, so I will use the same notation here. So instead of this one, I will write it once again. If you can bear with me, dEcV by dt, that will be equal to Q dot minus W dot plus mi times hi plus vi squared by 2 plus zi minus m dot h dot plus v dot square by 2 plus of g z dot. Now we have already seen that it is in steady state, so this will be 0. Again, in our this case, there is no heat loss or work done and diffuser work done unless it is given. It's not a work absorbing or work producing device, so mostly the work done always stays as 0. So here also my work done will be 0, so my heat received or heat added to the system or removed from the system will be 0, and work done by the system or whatever work done is always equals to 0. So we are left with this one. Now again we know that mi dot is equals to m0 dot, so what I can write it is here as only mi dot, that will be equal to h1 minus h2, h1 minus h2 plus vi square minus v dot square by 2, and also I can write it as g zi minus z dot. Okay, so this is what is left here. Now again, it is not saying us anything about the height of the two, the inlet and the outlet height. It is not saying anything. That means the diffuser height is very less, so that's diffuser height is there is no change in potential energy, so this part we can neglect. Okay, so what is left, we are left with this one. Okay, and again what it is given to us that v0 is entirely negligible, so this will be also equal to 0, so this will leave us the final expressions as h1 minus h2 will be equal to vi square by 2. Okay, now h1 I can write as cp t1 minus t2, ti dot, I should use the same notation, I'm sorry, this should be 0 and this should be 0. Okay, so ti minus t0, and this will be equal to vi squared by 2. Okay, from here I can write as t0 is equals to ti minus ti minus vi squared by 2 times of cp. Okay, so we have ti, that is 293. Okay, we have vi, that is 300. Okay, and we know the cp value of air, that is 1001. Okay, 0.1. now we put these values, what will we get? 300 square divided by 2 into 1001.1. okay, minus 293. So our answer will be 248.04 Kelvin. So this is our answer. Okay, now let us move to the next question. The turbine is operating under steady flow conditions, receives steam at the following state. Steam given is pressure 13.8 bar, specific volume 0.143 meter cube per kg, internal energy is 2590 kilojoule per kg, and velocity is 30 meter per second. The state of the steam leaving the turbine is also given, pressure is blah blah blah, internal energy is this one, velocity this one, heat loss is given, the rate of steam flow, that is whatever we calculated last, that is given to us. Now power developed by the turbine, remember in the last case the diffuser has no any work power. This is also very simple for us. Okay, so this is also very simple for us. Now what is given, let us just draw the diagram to make the conditions clear. Okay, now this is my state 1 for my turbine, and this is my state 2 for the turbine. and here it will go this side, it will go from here, and my work of the turbine, I need to calculate my work for the turbine. Okay, and what it is telling us that it is losing heat Q dot, it is given as 0.25 kilojoule per second. Okay, that means this much kilowatt heat is lost, kilojoule per second heat is lost. Okay, now we need to find it this one. Okay, so the initial conditions are given to us. P1 is 13.8 bar, so I'm converting everything into kilopascal, so that R and everything will be like okay, since it is kilojoule is given, so 13.8 into I think 10 square, it will be kilopascal. Okay, and V1, that means volume, it is given to us as 0.143 meter cube per kg, and U1, internal energy, is given to us, it is specific internal energy is given to us 2590 kilojoule per kg, and velocity C1, let us take this as C1, it's given to us as 30 meters per second. Then P2 is given to us as 0.35 into 10 square kilopascal, and V2, that is my volume, specific volume V2, is given to us as 4.37 meter cube per kg. Then U2, internal energy, is given to us as 2360 kilojoule per kg, and our velocity C2 is given to us as 90 meters per second. So velocity is increasing there. Heat lost, I have already written there, and steam flow rate, that is m dot, and nothing is saying, so it will be remaining constant, it is given to us as 0.38 kilojoule per second. Now we are not required to calculate the mass flow rate, so we will directly move into the energy equation. Okay, so once again the energy equation is dE CV by dt is equals to Q dot minus W dot plus M1 H1 plus C1 squared by 2 plus G Z1 minus M2 H2 plus C2 squared by 2 plus Z Z2. Now we don't have H directly, but what we know, H is equals to U plus P into V. So we will put these values and we'll get this. So since this is a steady state, it's already given steady flow conditions, so that's why my this part will be 0, and this is given to us. Now we need to calculate this one, so we'll put this one aside. So this will give us W dot will be equal to Q dot minus, now M1 and M2 are same, so I'll put this as M dot, sorry, plus M dot times H1 minus H2 plus C1 squared minus C2 squared by 2 plus Z of Z1 minus Z2. Now once again, it is not telling us anything about the change in potential energy, so we will also take this as 0. Sorry. H1 minus H2. So now then my W dot will be Q dot minus what was the expression, Q dot plus m dot h1. H1 is equals to u plus pv, so it will be u1 minus u2 plus u plus pv. Na p and v are also changing. Okay, so u1 minus u2 will come out, then p1 v1 minus p2 v2, p1 v1 minus p2 v2. This part is your h1 minus h2 plus c1 squared minus c2 squared divided by 2. Okay, we'll put everything here now. Now I know what is the value of q. Okay, I know the value of q. My q value is q, yeah, 0.25. okay, and remember this is loss, so I'll put it as minus here, plus what is my m dot? My m dot is 0.38. 0.38. Then next is my what? u1 minus u2. What was my u1? 2590. 2590. And my u2 was 2360. 360 plus p1 v1. p1 is 13.8 into 10 square into v1 is 0.143 minus p2 is my 0.35 into 10 square into my v2 is 4.37. p1 v1 minus p2 v2 plus c1 squared minus c2 squared, so this will be 30 squared minus 90 squared by 2. Okay, so I'll put all these stuffs here, so you'll get this one as minus 3325.6 kilojoule. It will be kilowatt, I'm sorry, it will be kilowatt, minus 3325.6 kilowatt. This will be the answer. This will be the power developed by the turbine. Okay, now at steady state, steam turbine produces 1050 megawatt by letting the pressure down from 50 bar to 1 bar. The steam enters the turbine at 320 degrees Celsius with a velocity of 8 meter per second, and the mass flow rate is given again 150 kg per minute. The steam leaves the turbine with a quality of 0.94. Now we will be dealing with some factual effects, like when it enters it is in the steam state, but when it leaves it is not a proper steam, it's something a mixture of both steam and water. Okay, and the velocity of this one is given as 65 meter per second. We have to determine the rate of heat loss from the turbine to the surroundings in kilowatt. Now some things are given to us. This will be dealt very good in very details. Yeah, tell me.
So, is it possible? Means I have a doubt related to some concepts in thermodynamics. So, will you please tell me about that?
Can we discuss this after the class? Because or else I can put a doubt class once, it's okay, but right now we are supposed to complete your this related numericals. Okay, I will finish these numericals first and then I will clear. You will be there till the last.
Yes, sir. Yes, sir.
What doubt you have, by the way?
So, related to some concepts like thermal capacity, specific heat, calorific value, internal energy, and enthalpy.
Okay, fine. These are some basic things, but let me finish these sums. Okay, if I have time today I will do that. After if not, then I will take a doubt class. Okay, there is I mean, say 3 weeks are over, so in the next class I will take fewer sums, and then I will put at least half an hour for clearing your doubts. Okay, and in the meantime, if you are unable to do that, you just send me a mail. Okay, I think you have my mail address. You just send me a mail there. I will reply, or I will fix a meeting with you.
Have that.
Okay, I will send you after this class. You just remember me. Okay.
Okay.
Yeah. So okay, then next is at steady state. Once again they are giving us a steady state. A steam turbine which produces a 1050 megawatt by letting the pressure down from 50 bar to 1 bar. The steam entering conditions are given, and the mass flow rate is given to us. The steam leaves the turbine with a quality of 0.94 and the velocity is given to us. Now we have to determine the rate of heat loss from the turbines to the surroundings. Now what I was telling about, yes, so steam table, these are all values that are taken from the steam table. Now this will be dealt in detail when you will be reading the chapter called properties of liquid water, I think. I forgot the chapter name. So in that it will be dealt how you will be looking at the steam chart. I will just give a quick hint how you will get the values there. Now so this is the same as usual, but the only thing is there we are getting a mixture of steam and water in one case. Okay, now what happens, again this is my inlet condition 1 and then this is my outlet condition 2. Okay, and my initial P1 is given as it will be 50 into 100, sorry, 10 to the power 2 kilopascal, and then my T1 it is given as 320 degree Celsius, and my velocity C1 it is given as here it is, let me not confuse it, here it is not given any volume, so I'm directly use it V is given as 8 meter per second, and my mass flow rate is given, nothing is said, so steady state it is telling, so inlet mass flow rate will be always equal to the outlet mass flow rate. We have already seen in question number 1. So 2.5 kg per second mass flow rate is given to us. Now outlet pressure condition is also given. P2 is equal to 100 kilopascal, and my T2 temperature, I think we need to determine the rate of heat loss from the surrounding. Okay, T2 is not given to us, that is a question mark. And what thing is not given to us, velocity is given. Okay, velocity is given as 65 meters per second, and x2. Now what is this x2, we will learn just a bit of it. Okay, now let me try to visualize this. Suppose steam entered here. Okay, it was a superheated steam. How will we know that? Oh, what is coming, let me wait. Is someone trying to join? No. Okay, fine. Yeah, so here it is directly telling us that it is for superheated steam, the values are this one and this one. Now there is this all things you will have to look in property diagrams also, because this is a pictorial view of what is happening. This is just a block diagram, but when you will be looking at the steam table, you have to understand at what state it is, whether it is in superheated steam state, or whether it is in liquid state proper, or whether it is in a mixture of liquid or both. Okay, so here a steam turbine, it is producing blah blah blah, the steam enters, it is telling. Okay, that does not mean that steam will always be in the superheated state. Now you have to find out whether it is in superheated state or not. Okay, so for that you have to look at the property diagrams. Now there are so many, you have already seen, I think, PV diagram. That is one famous property diagram, that is TV diagram. Okay, and in that TV diagram, the constant pressure lines we can draw. Okay, so this is the part where it is the I mean mixture of both the, I mean to the left of this dome it is the liquid phase, and to the right of this dome it is the gaseous phase. Okay, and the constant pressure lines look this way in this graph. These are my constant pressure lines. Okay, these are my constant pressure lines, and pressure increases this side. I mean, if this is P1 and if this is P2, then P1 must be greater than P2. This is how my TV diagram looks. So from here I will explain you how it is going on. Now see, from 50 bar it is coming to 1 bar. That means initial state 50 bar, and it is going to, so it will be, if I'm taking this one as 50 bar, so then this P2 must be my, this one as 2 bar, oh sorry, 1 bar. Okay, and from here to here expansion is taking place. Now let me just draw it nicely. Now suppose this was my first point. Okay, this has some temperature value and this is some pressure. Say this temperature is my what is my this temperature, say 320 degrees Celsius, 320 degrees Celsius. So at this constant pressure at this temperature. So this will be my point of intersection, and this is my first state number 1. This is my state point number 1. Now from this state point number 1, expansion is taking place to this pressure curve. Now it may take this way, it may take this way, it may take this way, it may take a curved way, it may take a curved way, we don't know this. Okay, it will tell us everything from the process. Okay, now but right now it is not mentioning us anything, so we will just draw a curve. Now I will draw this again since it's becoming a messy stuffs. Okay, yeah, let me put one more, it will be better. Okay, yeah, so so let me draw this dome shaped, and this is T and this is V. Now this is my constant pressure first pressure line, this is my P1, and this is my P2 suppose. Now before going to this, how we come to know that at pressure P is equals to 50 bar and temperature T equal to 320 degrees Celsius, how we know that it is a superheated steam? Okay, this will be discussed in detail, but I'm just telling you, you have to first of all go in the steam table and check the what you call saturation temperature, the saturation liquid temperature there, and if this temperature is greater than this one, then it will be in the superheated state, otherwise it will be in the liquid state. It will be dealt in detail, I'm just telling you. Now here it is directly giving in the question, so we need not need to worry. At 50 bar and 320 degrees Celsius, my enthalpy of the superheated steam is given as 2986.2. So if this is my state 1, okay, from state 1, now expansion is taking place such that it is not purely steam, that is why some x value is given. Okay, at this state it expansion is taking place, state number 2. Now don't think it is a straight line, or I'm drawing any arbitrary line such that it is not a pure steam. Because why I'm not drawing it as a pure steam? I'm not drawing it as a pure steam because because here an x value is given to us, here x of 0.94, that means 94% is only vapor, 94% of vapor is only present. Okay, the rest 6% is liquid, that means it is a mixture of both liquid and vapor phase. So it will fall in this dome, and I can't go more this side because 94% now, so more part should be steam and less part should be your what you call liquid. Okay, so this is my state 2 and this is my pressure P2. Okay, now how will I first of all I need to write the energy equations. Why? Because I have to calculate, I think, the heat loss. So that's why if I have to calculate the heat loss, I should not go with the mass flow rate equation, because mass flow rate is already given to us. No use of showing the mass flow rate. We can only show mi dot is equals to m2 dot, which we know because this is a steady state. Okay, now let me write dECV by dt, that will be equal to my q dot minus w dot. I will write this as 1 h1 minus h2 plus c1 squared minus c2 squared, I'm sorry, forgot the notation, v1 squared minus v2 squared by 2 plus g of z1 minus z2. Okay, now we can neglect this part because z part is not given to us, so we can again cut this part. Now heat loss, is it given to us? I think heat loss I have to calculate, and work output is given to us, and we need to find h1 h2. Now what is h1? H1 is simple, because at this state everything is given to us, that at superheated steam this 50 bar and 320 degrees Celsius here. Okay, at superheated state the value is h equals to 2986.2 kilojoule per kg. So my h1 is 2986.2 kilojoule per kg. Now calculate, now we have to calculate the h2. Okay, this 2 value is here, so it is a mixture of both liquid and this one. Okay, so at the pressure P2, at the pressure P2, that is 1 bar, hf is given to us and hg is given to us. Now let me show you where is my hf. my HF will be here because F stands for fluid, that means the not I mean that liquid state, and this is my Hg. Okay, the energy, the enthalpy up to this point is Hg, the enthalpy from left up to this point is Hf. Okay, and I need to calculate H2. So what will be my H2? My H2 will be Hf plus x into Hg minus Hf, because x part is only my vapor. Okay, so H into Hg minus Hf will be giving my this part, and this part into vapor will be giving your this one. So what is my Hf? My Hf is 417.5, 417.5. My x is 0.94, I guess, and my Hg is 2674.95, 2674.95 minus 417.5. Okay, so from here I can calculate my H2. So this will give my H2 H2 2674.95 minus 417.5 into 0.94 plus 417.5. Okay, so 25, it will be 2539.5, 2539.5 kilojoule per kg, 2539.5 kilojoule per kg. This is my H2. So I am done with H1, I am done with H2. Is it C1 and C2 given to us? C1 is given, I mean V1 is given to us, V2 is given to us. Yes, so we can calculate the answer. Now V1 is 8 and V2 is my 65 meter per second. So I can put it here now, and since it is a steady state, this will be equal to 0. I need to calculate the heat, I think. So I will put Q dot aside. So Q dot will be equal to W dot minus of M dot H1 minus H2 plus V1 squared minus V2 squared by 2. Okay, so W dot is given, it is produced by turbine, so it will be W dot is positive since it is produced by turbine. So I will convert it into kilowatt. 1050 into 10 to the power 3 kilowatt. Okay, so this will be 1050 into 10 to the power 3 minus m dot 150 kg per second. Okay, so 150 kg per minute. So 150 by 60 into 150 by 60. This is what okay, so and this H1 minus H2. H1 is 2986.2 minus 2539.5 plus C1 squared, that is V1, it is 8 squared, minus V2 squared is 65 squared by 2. Okay, so let me calculate this. Okay, 1085, this one. Okay, yeah, this will be almost equals to minus 61.59 kilowatt. Now negative stands for the heat is lost from the systems to the surrounding, and my system here is my turbine. Okay, now the next part is refrigerant. 134A, it enters the capillary tube of a refrigerator as saturated liquid at 0.8 megapascal. T saturation 31.31 degrees Celsius is given. HF HF 95.47 is given, Hg, oh okay, at that pressure, see T saturation is given. That's what I told. At that pressure you have to first check in the table, in the previous question you have to check, and if you check you will get that at that case, that is at 50 bar. If you will check for the T saturation, it will be less than 320 degrees Celsius. Okay, so that's how you know that this is a superheated steam. Now then T saturation is given to us, 0.8 megapascal T saturation is given to us, and it is throttled to a pressure of your 0.12 megapascal, and at that state now T saturation is given to us, HF is given to us, and Hg is given to us. Now we have to determine the quality of the refrigerant. In the previous case, that X that was given to us, now we need to calculate the X at the final state. That means I have to calculate the X2. Okay, suppose this is my throttling device. Okay, this is how they show a throttling device. Okay, this is my throttling device, and this is my initial condition, I mean the starting point, and this is my final state. Okay, so at P1 is given as 0.8 into 10 to the power 3 kilopascal, and P2 is given to us as 0.12 into 10 to the power 3 kilopascal. Okay, so it is throttling, and that means there is decrease of pressure is taking place, so we have to calculate the final state at which it is coming out. Okay, now yeah, so nothing is given, so we can assume it is a steady state. So assuming steady state, we know that if we assume steady state, the rate of change of mass of the control volume will be equal to 0, which will let us that the inflow mass rate will be equal to the outflow mass rate, that is m1 dot will be equal to m2 dot. Okay, and now the next equation is what? Our energy conservation equation, dE cv by dt will be equal to q dot minus w dot plus, I am putting this one as same m1 dot times h1 minus h2 plus v1 squared minus v2 squared by 2 plus g of z1 minus z2. Once again, nothing is mentioned about the potential energy, so I can directly write it as 0. Steady state, this is equal to 0. Heat flow, it is not telling us anything about the heat flow that's taking place or going out, so it will be equal to 0. Okay, and does it tells nothing about the work done also, so the work done will also be equal to 0. Okay, the work done will also be equal to 0, and the speeds are also equal to 0. Nothing is telling us, so they're neglecting kinetic and potential energy changes. What we are getting here finally is that m1 dot times h1 minus h2 will be equal to 0, which will lead us to the condition that h1 is equals to your h2. Okay, now this is a huge advantage because from here we can do a lot of stuffs. Now once again I am drawing this TV diagram. Okay, and say this was my initial pressure P1, and this is my final pressure P2. This is my initial pressure P1, this is my final pressure P2. Okay, and now a refrigerant enters the quality as a saturated liquid. That means what? It was there in this state. This is my saturated liquid state. Okay, this was my state number 1. Now then it is being expanded. Okay, it is being throttled and it is expanded to a pressure P2, and we have to calculate the quality now, so that means this will be a mixture, so I am directly writing it as expanding it to the case 2. Okay, so I need h1. What is h1? It is a saturated liquid now, so at this state hf will be my h1. Okay, h1 is what? hf at p1. Okay, and what is my hf at p1? Hf at p1 is 95.47 kilojoule per kg. Okay, then what is H2? H2 will be HF at P2 plus X2 times Hg minus Hf, and this both at P2. Okay, now what we know? We know Hf at P2, we know Hg at P2, we know Hf at P2, we don't know X2, but we can calculate it by using H1 is equals to H2. So I will put it here 95.47, and that will be equal to my Hf at P2 is what? 22.47. 22.47 plus X2, I need to calculate X2. Hg is 236.99 minus 22.47. So this will be your answer. That means X2 will be what? 95.47 minus 22.47 divided by 236.99 minus 22.47. Okay, so let me calculate this. 95.47 minus 22.47 divided by 236.99 minus 22.47. Okay, so your answer is 0.34. That means 34% water vapor is present in the state number 2. Okay, okay, so then let us move to the next part of our question. To the next question. A pump steadily draws water from a pond at a volumetric flow rate of 833 liters per minute through a pipe having 127 millimeter inlet diameter, and water is delivered through a hose terminated by a converging nozzle. The nozzle has an exit diameter of 25.4 millimeter and it is located at 10.7 meter above the pipe inlet. Now water enters at 20 degrees Celsius 1 bar and exits with no significant change in temperature or pressure. The magnitude of the rate of heat transfer from the pump to the surroundings is 5% of the power input. The acceleration of the gravity is 9.8 meter per second square. You have to determine the velocity of the water at the inlet and the exit, and you have to determine the power required by the pump. Okay, so what is given to us? That pump is drawing, okay, volumetric flow rate is given to us. Okay, so it is drawing at 833 liters per minute. So we'll convert this everything into SI. How you will get this one as 833 into 10 to the power minus 3 divided by 60. Okay, so this will give you in meter cube per second 0.0138 meter cube per second. Okay, then what it is giving as inlet diameter is given. So a I is equals to pi by 4 times di squared. Okay, so pi by 4 times di is 0.127 squared. Okay, so what will you get? 0.14 into 0.127 to 0.127. Okay, divided by 4. 0.012 meter cube, sorry, meter square, 0.012 meter square. Now water is delivered through a hose of a nozzle by a converging nozzle. The nozzle has an exit diameter. Exit diameter is also given, so I can calculate the exit area. That will be pi by 4 times the knot whole square. So that will be pi by 4 times 0.0254 squared. Okay, 254 0.0254 equal to divided by 4. Okay, 4 divided by 4, 0.005. Okay, that means 5 into 10 to the power minus 4, 5 into 10 to the power minus 4 meter square I'm getting. Okay, then what it is telling is that exit part, it is located at a height of 10.7 meters. Suppose this is my pump. Okay, and from here my nozzle that is taking out the water. Okay, this height is 10.7 meter. Okay, water enters at 20 degrees Celsius and 1 bar, so P1 is equals to 1 bar, and T1, I mean inlet, is 20 degrees Celsius, and with no significant change in temperature and pressure, that means P naught is equals to Pi, and T naught is also equals to your Ti. Okay, so the magnitude of the rate of heat transfer from the pump to the surrounding is 5% of the power input. Okay, so what does it mean? That Q dot, whatever it is nothing but 5% of W dot. That means whatever input it wants, a pump requires some input electric power, so that electric power 5% is lost in the terms of the heat. Okay, then the acceleration due to gravity we all know, so we have to determine the velocity of the water at the inlet at the exit. Okay, so okay, velocity of water at the inlet and the exit. So velocity of water at the inlet is very easy. So first one, what we require V1 or Vi. What is Vi? Vi is nothing but the volume flow rate divided by Ai. Okay, because volume flow rate, area into velocity is my volume flow rate, so area divided volume flow rate divided by area will give us this one. So what is Q? Q is given as 0.0138, and what is my Ai? It is 0.012. Okay, 0.0138 by 0.012, it is equal to 1.15 meter per second. 1.15 meter per second, that is my velocity area at the inlet. Okay, now what it is telling, water pump flows steadily. Okay, so we know, let me take one more slide. Okay, so we know that steady state dmcv by dt is equals to what? Mi dot minus mo dot. So steady state, this part will be 0, so this will give us as mi dot will be equal to mo dot. Okay, so mi dot is what? Rho I a I vi, and mo dot is rho dot a dot v dot. Okay, so now do I know ai? I know ai, I know vi, I know v naught, I know a naught. I need okay, I need to calculate v naught. I don't know densities. Now yeah, one thing it is telling us, since no significant change in P and T, therefore what we can write as rho I is approximately equal to rho naught. So this reduces the mass conservation equation to AIVI is equal to A naught V naught. So from here V naught will be equal to AI by A naught times VI. Okay, so that is what? Pi by 4 into, okay, I forgot the value, pi by 4 okay, I have calculated only 0 0.012, 0 0.012, 0 0.012. Here it is 5 into 10 to the power minus 4 into Vi is my 1.15. Okay, okay, so 0.012 into 1.15 into 2 3 4, okay, divided by 5. That is my output velocity is 27.6 meters per second. Okay, so next is what my power required by the pump. So I'm done with the inlet and the exit velocities by the mass conservation equation. Now I need to calculate the power output. So for that, once again I'm going for the energy balance equation. Okay, so for the part B, d e cv by dt, that will be equal to q dot minus w dot plus, once again, the same mass flow rate, so that will be m dot into h1 minus h2 plus v1 squared minus v2 squared by 2 plus z1 minus z2. Now in this case, remember the all other previous cases we had z1 and z2 at the same height, so we neglected the change in potential energy, but in this case we cannot neglect the change in potential energy. Okay, but one thing we can neglect here, because since there is no significant change in pressure and temperature, so cpt1 will be equal to cpt2, so h1 minus h2 will be 0, steady state, so this part will be equal to 0. Okay, q dot is given to us as 5% of w dot, and we know v1 squared and v2 squared. Okay, so what we will do, we need to calculate what, we need to calculate w dot. Okay, so this will give us 0 will be equal to 0 0.05 of w dot, because it is 5% of w dot minus w dot plus m dot v1 squared minus v2 squared by 2 plus z of z1 minus z2. Okay, so from here I can write this will be 0 minus 0 0.95 w dot, 0.95 w dot is equals to my m dot. I think I know what is my value of m dot. My value of m dot rho. Okay, so from here you have to calculate the rho value also. So rho I is equals to p by r ti. Okay, oh, we don't need, because this is water now. So we know that water density is almost equal to 1000 kg per meter cube. Okay, so now this will be what, m dot is equals to into aivi, so 0 point, let me calculate m dot first. So m dot will be 1000 into 0 0.0138 into sorry, this will be your m dot, so this will be my 1 2 3 13.8 kg per second. Okay, so then this will be 13.8 times v1 squared. What is my v1? V1 is 1.15 squared minus v2 is your 27.6 squared, v1 squared minus v2 squared by 2 plus z of z1 is 0 and z2 is what, I'm taking this as 0. Okay, and so this z2 is my 10.7 10.7. Okay, put it all this, what you will get, w dot get W dot as obviously negative 6.899 kilowatt. Okay, now steam enters the condenser of a vapor power plant at a 0.1 bar. Once again, HF at 0.1 bar is given as 191.83 kilojoule per kg. Hg at 0.1 bar is given as 2584.7 kg kilojoule per kg, and quality of the steam is given to us as 0.95, and condensate exits at 0.1 bar and 45 degrees Celsius, where H is given to us as 188.45 kilojoule per kg. Now cooling water enters the condenser in a separate stream as a liquid at 20 degrees Celsius, where H is given to us, and exits at a liquid 35 degrees Celsius, which H is also given to us, and there is no change in pressure. Now heat transfer from the outside of the condenser and changes in kinetic and potential energies of the flowing streams can be ignored. Now for steady state operation, you have to determine the ratio of the mass flow rate of the cooling water to the mass flow rate of the condensing steam, and then you have to determine the energy transfer from the, okay, let us first calculate the first part. Now we have to first draw the figure. So there is a, okay, this is basically a heat exchanger. Okay, so this is basically a heat exchanger where this side, say I'm telling us that steam is flowing. Okay, so this is the states of steam, that is my 1, and steam going out at state 2, and then there is some cooling agency, in this case it is water. Okay, so it is coming from one side and it is going out from the other side. Okay, so this is how the apparatus will look like. So say this is my cooling water, it enters from here, and this is my cooling water which goes exits of the cooling water. Okay, so what it is telling that steam at 0.1 bar. Okay, at the point 1, P1 is given as my 0.1 bar. Okay, and at this state what is given as HF is this one and Hg is this one, and that quality of the steam is given to us x1 is equals to 0.95. so from here what we can calculate, we can calculate we know that HF, we can calculate H1. Okay, what will be my H1? H1 will be HF at 0.95 0.1 bar, HF at 0.1 bar plus x1 times Hg at 0.1 bar minus HF at 0.1 bar. Okay, so from here I can calculate HF is what? HF at 0.1 bar is this one. Okay, 191.83 plus what is my x1? X1 is 0.95 plus Hg is 2584.7 minus 191.83. Okay, what will be the value? 2584.7 minus 2584.7 minus 191.83. Okay, into 0.95 plus 191.83. okay, 2465.05 kilojoule per kg. Okay, someone is trying to enter, let me put him in. Okay, okay, so that is 2465 kilojoule per kg, that is my H1. Next is okay, I'm sorry, yeah, Next, cooling water, okay, and condensate exits at 0.1 bar and 45 degrees Celsius. So what it is telling us that it is exiting at a condensate, okay, it becomes a condensate and it exits. So at P2 is given to us as 0.1 bar only, and T2 is given to us as 45 degrees Celsius. Okay, and it is also telling that at this state it is condensate, it means it's liquid state, and its enthalpy is also given to us, that is H2 is equal to your 83 point, I'm sorry, 188.45 kilojoule per kg. Okay, so 1 and 2 it's done, that means the steam part is done. Now next part is your cooling water. It enters the condenser in a separate stream, that's what I have showed. Okay, cooling water is entering and it enters at 20 degrees Celsius and with no change in pressure, that means the pressure is again 0.1 bar. Everything is done here in 0.1 bar. Okay, I'll add one more slide. Okay, so at that, what it is telling that cooling water enters the condenser in a separate stream at so T3 P3 is also equal to 0.1 bar, and T3 is equal to your 20 degrees Celsius. So at this state your H3 is given to your given to us. H3 is given to us as 83.92 kilojoule per kg. Okay, 83.92 kilojoule per kg. Okay, and next what it is telling that an exits as a liquid, again liquid 35 degrees Celsius it exits. So P3 is again 0.1 bar and T3 is your 35 degrees Celsius, and your H4 sorry P4 H4 35 degrees Celsius, 35 degrees Celsius, 146.65 kilojoule per kg, that is 146.65 kilojoule per kg. So the first question now comes, now then heat transfer from and outside the condenser, that means there is no heat transfer throughout this system, that if you take this to as one system, so there will be no heat transfer take place and there will be no changes in kinetic and potential energy take place from this system. Okay, so from then you have to calculate the mass flow rate, the ratio of the mass flow rate of the cooling water to the mass flow rate of the condensing steam. Okay, so now we always consider in the steady state. Okay, so in the steady state what will be happen, dmcv dot dt, this will be equal to 0. Okay, so if there is no change in the steady state, so inflow of the steam rate should be equal to outflow of the steam rate, and inflow of the water state will be equal to outflow of the water state. Okay, since there is no change in that means the steady state, now we will apply the energy conservation. Okay, is equals to q dot minus of w dot plus we can write anything now, this one m1 dot we will write, this will be h1 minus h2 plus v1 squared minus v2 squared by 2 plus z1 minus z2. Okay, this is for the steam part. Next is for the liquid water part, I can write any one, I will write just m3 dot, this will be equal to h3 minus h4 plus v3 squared minus v4 squared by 2 plus z of z3 minus z4. Okay, now what it is telling us, it is telling us that it is in a steady state, so this will be equal to 0, there will be no heat loss, that is equals to 0, there will be no work transfer, that will be equal to 0. the changes in kinetic and potential energies are also negligible. So that's why the changes in kinetic and potential energies for both the system, I mean both for the entire system, that will be equal to 0. Now then this gives us what? It gives us that m1 dot into h1 minus h2 plus m3 dot into h3 minus h4. Okay, so from here what we require to find out, we are required to find out the ratio of the mass flow rate of the cooling water to the mass flow rate of the condensing steam. That means we require to find out m3 by m1 dot. Okay, so can we write this one? M3 will take this one this side, it will be m3 dot into h1, so it will be h1 minus h2 divided by h4 minus h3, if I am correct. H1 minus h2 minus h2 minus, okay. So what are the values of h1? So h1 value is 2465.05, 2465.05 minus my h2 is 188.45, 188.45. My h3 is 83.92. I need h4, sorry, 146.65, and my h3 is 83.92. So put all these values, you'll get your answer. Okay, so 2465.05 minus 188.45 divided by 146.65 minus 83.92. Okay, so the answer is 36.29. so this is the required ratio. Okay, now the next part is the energy transferred from the condensing steam to the cooling water in kilojoule per kg of steam passing through the condenser. Okay, so in the second part we require to find out the condensing steam, the energy transferred from the condensing steam to the cooling water. That means how much heat is transferred from the steam to the cooling water. Okay, that one we require to find out in the next part. Once again, let me add one slide. Okay, yeah, so in the second part we will take let control volume be our steam part. Okay, then what will happen, that DECV by dt, that will be equal to again QCV, I mean that is Q dot minus W dot. Okay, plus M1 dot, sorry, H1 minus H2 plus V1 squared minus V2 squared by 2 plus Z1 minus Z2. Okay, now this is what, this is again in steady state, so this will be equal to 0. There will be no changes in kinetic and potential energies as it is mentioned here. And one thing is there, that this work done again it is not 0, but this time this Q will not be equal to 0. Why? Because this Q is the for the heat exchange from the steam, it's not from the system both combined. Okay, so there will be some Q, and that Q we need to find out, and that Q is equals to what? Q dot is equals to M1 dot times H2 minus H1. Oh, what is happening? I need to rub it. M1 dot times H2 minus h1. Okay, so what is, and wait a minute, what you need to find out, you need to find out in kilojoule per kg. Okay, so in kilojoule per kg, that means in per kg it will be q dot by m1 dot is nothing but h2 minus h1. So what is h2? h2 is 188.45, 188.45 minus, and what is h1? h1 is 2465.05, 2465.05. okay, that is kilojoule per kg. Okay, so you will get this 188.45 minus 2465.05, so it will be minus 2276.6 kilojoule per kg. Okay, so this is the answer. Now a rigid tank contains air. It consider as an ideal gas, even if they don't say, we'll consider unless it is mentioned as a real gas. It has a temperature T1 and pressure P1. A pipeline through which air flows at a temperature Ti and pressure Pi is used to fill air into the tank via an adiabatic valve. The walls of the tank are insulated. Find an expression for final temperature of air in the tank. Also fine. Okay, we'll do the second part later. Let us come to the first part. Okay, now suppose this is a tank. Okay, and this is my valve. Okay, this is my valve, and there is something there, this air is flowing, and this temperature and pressure of the air is Ti. Okay, and from here uh, through this valve air is being filled inside. Okay, so it is being filled inside such that if it is initially at T1 and P1, after filling, what happened? After filling, okay, the same TIPI it was going on. After filling, it went to T2 and P2 state. Okay, so we have to calculate an expression for the final temperature T2. Okay, now let us first do the mass balance. Okay, so let me first do the control volume. If you will get, this is my control volume, this is my control volume. Okay, this tank, this rigid tank is my control volume. Okay, this rigid tank is my control volume. Okay, so now d of m cv by dt, that will be equal to what? My mass inflow dot minus mass outflow dot. Okay, so what will be my mass inflow dot minus mass outflow dot? And then mass inflow dot is nothing but okay, we don't know that one. Now this is not in a steady state. Why this is not in a steady state? Because with the passes of time, this air will fill, and filling of this air will change this temperature and pressure. So for the first time we are dealing with an unsteady open flow system. Okay, so this is a case of unsteady open flow system. So this dmcv by dt, this will be what? This will be m2 minus m1. Okay, so this m2 minus m1 will be what? mi dot minus mo dot. So this one I can write, this one is m2 minus m1 dot. I can write this one because everything is in the rate of change. Now there is entry from this point, but there is no exit from this point. So what I can write as m0 dot is equals to 0, and so from here what you can write is uh, that m1 dot is equals to m2 dot minus mi dot. Okay, m m1 dot is equals to m2 dot is equals to mi dot. Okay, now next part is, oh, it's the end of the slide. Okay, so then we have done an equation for mass flow rate. Now we will do the energy balance. So d e cv by dt, that will be equal to q dot minus w dot plus mi dot hi plus vi squared by 2 plus gzi minus mo dot plus h2 plus v sorry ho plus vo squared by 2 plus zzo. Now we already know that there is no mo dot, so this will be equal to 0. There is no any work transfer, this will be equal to 0. There will be no any heat transfer, this 2 will be equal to 0. Work and heat transfer not equal to 0. But this time dECV by dt will not be equal to 0, because this is my control volume is in unsteady state. So dECV by dt I can write this as nothing but energy at the second state minus energy at the first state. Okay, energy at the second state minus this one will be energy at the first state, and this I can write is as, okay, and again if the kinetic and potential energies are very less as compared to this enthalpic energy, so what I can write this one as mi dot hi, okay, mi dot times hi. Now E2 minus E1, energy it is compressed. Now if I will again delta ke and delta pe is equals to 0 for the system, then the energies will be expressed in terms of what? Internal energies only. So this equation will become m2 u2, that is the final internal energy, minus initial internal energy, and that will be equal to my mi dot times hi. Okay, so m2 u2 minus m1 u1, this will be mi dot, I have written this one as m2 dot minus m1 dot times hi. Okay, so from equation from the previous equation I know this. Now again u for an ideal gas we know that u is equals to cv, so m2 cv t2 minus m1 cv t1, that will be equal to m2, let me write it dot, m2 dot minus m1 dot times cp ti. Okay, now from here what I can write it as m2 t2 minus m1 t1, this will be equal to m2 dot minus m1 dot into cp by cv times ti. Okay, now we know that in an ideal gas pv is equals to mrt. Okay, so from here m is equals to pv by rt. So using this, what I can write is as, okay, this one p2 v2 by rt2, oh, this will not be, yeah, p2 v2 rt2 minus okay, into t2 minus p1 v1 by rt1 into T1 is equals to M2 dot minus M1 dot times Cp by Cv is equals to, okay, I can write this one also is the same thing, P2 V2 by R T2 minus P1 V1 by R T1 times gamma of Ti. Okay, next I can write this as P2 minus P1 times V. Why? Because this is a rigid tank. Since it is a rigid tank, so V2 is equals to V1 is equals to V. So this T2 will get cancelled. I can cancel all the R's. So and this it will remain as P2 minus P1 into V, and that will be equal to P2 by T2 minus P1 by T1 into V into gamma into Ti. Okay, this V is also getting cancelled. Now then final expression will be your P2 by T2, that will be equal to P2 minus P1 by gamma times Ti plus P1 by T1. Okay, so then this P2 minus P1 into T1 plus P1 into gamma Ti. This is just by taking the LCM, and that will be equal to gamma Ti T1. Okay, so then this one I can write as P2 T1 plus P1 into gamma Ti minus T1 divided by gamma Ti T1. Okay, so again then what I can write this one as T2 by P2 will be equal to gamma times wait a minute, I can gamma times Ti T1 divided by P2 T1 plus P1 gamma Ti minus T1. Okay, so then this one gamma Ti T1 P1 plus P1 gamma Ti by T1 minus 1. Okay, so and finally gamma Ti by 1 plus P1 by P2 to the power gamma Ti T1 minus 1. Okay, now this is the final expression for your this is T2 by P2, and you put this one as T2. Okay, so this is the final expression of the temperature, if this one final expression for the temperature in all the states. Now the second case is that if the tank is initially evacuated, so if the tank is initially evacuated, so there will be no pressure in the first state. So initially evacuated, then P1 is equals to 0. So putting this, if you put P1 is equals to 0, then your T2 expression becomes gamma times T1 gamma times Ti divided by 1 plus 0. This entire thing is 0, so this will be gamma times Ti. Okay, so this is your answer. Okay, thank you for attending to this class.